A single lightning bolt can heat the air to temperatures hotter than the surface of the sun and release an enormous burst of energy in less than a second. But have you ever wondered what lightning actually is? Is it really just one bolt striking the ground during a storm? Or is there much more happening above us than we can see? The truth is that lightning comes in many different forms. Some flashes stay hidden inside clouds, some stretch across the sky between storms, others strike the ground with incredible force, and a few even shoot upward toward the edge of space. So, how many types of lightning are there, and what makes each one different? To understand that, we need to start with the most common form of lightning and work our way up. Level 0, intra-cloud lightning. The most common type of lightning never touches the ground at all. This form is known as intracloud lightning, often abbreviated as IC lightning. Instead of traveling from a cloud to the Earth's surface, the electrical discharge occurs entirely within the same cloud. In fact, scientists estimate that most lightning flashes during thunderstorms are intracloud events. Inside a thundercloud, complex air currents continuously move water droplets and ice crystals upward and downward. As these particles collide, electrons are transferred between them, gradually separating positive and negative electrical charges. Over time, the cloud develops distinct regions of charge, with negative charges typically concentrated in the lower portion of the cloud and positive charges accumulating higher up. As the electrical difference between these regions grows stronger, the air eventually becomes unable to resist the electric field. When the electrical pressure becomes strong enough, a lightning discharge forms inside the cloud. The lightning channel connects areas of opposite charge, allowing electrons to rapidly move through the atmosphere and neutralize the imbalance. Because the lightning remains hidden inside the cloud, people on the ground usually cannot see a clearly defined bolt. Instead, the cloud appears to light up from within, producing a bright flash that illuminates large portions of the sky. This glowing effect is often referred to as sheet lightning, although the actual lightning channel is still moving within the cloud. Intracloud lightning can travel significant distances inside the cloud structure. The discharge may branch repeatedly as it moves through different regions of electrical charge. In some cases, the lightning spreads horizontally across large portions of the storm system. These flashes play an important role in regulating the electrical balance inside thunderstorms. Without them, the buildup of charge inside clouds could grow even stronger. By releasing electrical energy internally, intracloud lightning helps stabilize the storm's electrical environment. Even though intracloud lightning is extremely common, it is often overlooked because the flashes are partially hidden by cloud layers. However, when viewed from aircraft or satellites, these lightning discharges can create spectacular patterns of glowing channels spreading across the storm cloud. Level 1, cloud-to-ground lightning. Cloud-to-ground lightning is the type of lightning most people immediately recognize. This occurs when an electrical discharge travels from a thundercloud down to the Earth's surface. Because the bolt connects directly with the ground, it can cause significant damage to structures, trees, and electrical systems. The process begins when negative charges accumulate near the bottom of a storm cloud. These charges create a powerful electric field between the cloud and the ground below. As the electric field grows stronger, positive charges begin gathering on objects at the surface, including buildings, trees, and even the ground itself. Eventually, the electrical difference becomes strong enough to overcome the insulating properties of air. At this point, a faint channel of ionized air called a stepped leader begins moving downward from the cloud. This channel does not travel smoothly, but instead advances in rapid steps, branching out as it searches for the easiest path toward the ground. As the stepped leader approaches the surface, positive streamers begin rising upward from objects on the ground. These upward moving channels of charge attempt to connect with the descending leader. When the two channels finally meet, a powerful surge of electricity travels upward along the path that has formed. This surge is called the return stroke, and it produces the brilliant flash of lightning that we see. The return stroke heats the air along the channel to temperatures of around 30,000 degrees Celsius. This sudden heating causes the air to expand explosively, creating the thunder that follows a lightning strike. Cloud-to-ground lightning often contains multiple pulses of electricity traveling along the same path. After the first return stroke fades, additional strokes may follow along the ionized channel, causing the lightning bolt to flicker rapidly. Because these strikes connect directly with the surface, they can have serious consequences. Lightning can ignite fires, damage buildings, disrupt electrical grids, and pose serious danger to people caught outdoors during storms. Despite these risks, cloud-to-ground lightning represents only a portion of all lightning activity during thunderstorms. Level 2. Cloud-to-cloud lightning. Another form of lightning occurs when electrical discharges travel between separate storm clouds. This type is known as cloud-to-cloud lightning. In large storm systems where multiple thunderclouds form close together, each cloud can develop its own regions of electrical charge. When the electrical difference between neighboring clouds becomes strong enough, a lightning channel may form connecting them. This allows electrical charges to move between the clouds, helping balance the electrical environment within the storm system. Cloud-to-cloud lightning can produce long, horizontal flashes stretching across the sky. Sometimes, these lightning channels extend for many kilometers as electricity travels between towering storm clouds. Because these discharges often occur high in the atmosphere or behind thick cloud layers, they may appear less dramatic from the ground. However, from aircraft flying near storms or from satellites observing from above, cloud-to-cloud lightning can appear as vast networks of branching electrical channels connecting different parts of a storm system. These lightning discharges are especially common in large thunderstorm complexes where many storm cells develop close together. By transferring electrical charge between clouds, this type of lightning helps maintain electrical balance across the entire storm system. Although cloud-to-cloud lightning rarely strikes the ground directly, it still represents an important part of the complex electrical activity occurring inside powerful thunderstorms. Level 3. Positive lightning. Most cloud-to-ground lightning carries negative electrical charge from the cloud down to the ground. However, in some cases, lightning can carry positive charge instead. This type of lightning is known as positive lightning, and it is often far more powerful than typical lightning strikes. Positive lightning usually originates from the upper regions of a thundercloud, where large concentrations of positive charge build up. Because this region is higher in the cloud, the lightning channel must travel a longer distance before reaching the ground. These strikes often occur at the edges of storms or even several kilometers away from the main rainfall area. Sometimes positive lightning strikes happen when the storm appears to be moving away, catching people off guard. Positive lightning typically carries a much stronger electrical current than negative lightning. The discharge may contain several times more energy than a typical lightning strike. Because of this, positive lightning is responsible for many lightning-caused wildfires and severe damage to electrical infrastructure. Another unique feature of positive lightning is that it often produces a single powerful flash instead of multiple rapid pulses. The intense energy released during these strikes can create exceptionally loud thunder and extremely bright lightning bolts. Although positive lightning accounts for only a small percentage of total lightning activity, its strength makes it one of the most dangerous forms of lightning during thunderstorms. Level 4. Forked lightning. One of the most visually recognizable forms of lightning is forked lightning. This is the dramatic branching lightning often captured in photographs of thunderstorms, where a bright bolt splits into multiple jagged paths as it moves through the sky. Forked lightning usually occurs in cloud-to-ground or cloud-to-cloud discharges when the lightning channel divides into several branches while traveling through the atmosphere. The branching happens because lightning does not travel in a straight line. As the stepped leader moves through the air, it constantly searches for the path of least electrical resistance. The atmosphere is not uniform. It contains variations in temperature, humidity, air density, and electric charge. Because of this, the electrical channel often splits into multiple paths as it moves forward. Some of these branches fade away, while others continue growing until one eventually connects with the ground or another charged region. When the return stroke travels along the ionized channel, all of the branches briefly glow with intense brightness. The result is the dramatic tree-like pattern often associated with lightning bolts. These branching shapes can stretch across large portions of the sky, sometimes covering several kilometers in width. Forked lightning is often associated with powerful thunderstorms where strong electric fields and turbulent winds create complex pathways for electrical discharge. The branching patterns may may change with each pulse of the lightning flash, giving the bolt a flickering or dancing appearance as multiple return strokes travel through the same network of channels. Because the lightning channel branches outward, it increases the area where the strike could potentially connect with the ground. This means that forked lightning can sometimes strike objects at unexpected locations within the storm's electric field. The branching patterns seen in forked lightning are a striking reminder that lightning is not simply a straight bolt of electricity, but a complex electrical network spreading through the atmosphere in search of a conductive path. Level 5. Sheet lightning. Sheet lightning is a type of lightning that appears as a broad flash illuminating large sections of the sky rather than as a visible bolt. During sheet lightning, the clouds suddenly glow with light, sometimes lighting up the entire sky for a brief moment. Although it may look different from typical lightning bolts, sheet lightning is usually caused by lightning occurring inside or behind clouds. In most cases, sheet lightning is actually intra-cloud lightning that is hidden from view. When the lightning channel forms within the cloud, the surrounding layers of water droplets and ice crystals scatter the light from the discharge. Instead of seeing the lightning bolt itself, observers on the ground see the cloud glowing from within. This effect is particularly common when thunderstorms are distant or partially obscured by cloud layers. Even if the lightning bolt itself is hidden, the intense flash still illuminates the cloud structure, creating the appearance of a large glowing sheet of light across the sky. Sheet lightning can also occur when lightning flashes behind thick cloud banks or along the horizon where the storm itself may not be clearly visible. Because the lightning channel is concealed, the flash appears softer and more diffused compared to the sharp, bright lines seen in forked lightning. Although sheet lightning is mainly a visual effect rather than a completely different electrical process, it is still an important way that lightning is observed from the ground. Many storms produce numerous sheet lightning flashes as electrical discharges occur within the cloud structure. This type of lightning often appears during the early stages of storms or when thunderstorms are far away. The sky may flicker with flashes of light long before the storm arrives, offering a distant preview of the electrical activity taking place inside the clouds. Level 6. Ribbon lightning. Ribbon lightning is a rare form of lightning that appears as several parallel streaks of light across the sky. Instead of a single lightning channel, the bolt seems to consist of multiple ribbons placed side by side. This phenomenon occurs when strong winds push the lightning channel sideways between successive return strokes. A single lightning flash often contains several pulses of electricity that travel along nearly the same path. Normally, these pulses occur so quickly that the channel appears as a single bolt. However, when strong crosswinds are present within the storm, the ionized channel from the previous stroke may drift slightly before the next pulse occurs. When the next return stroke travels through the air, it follows a slightly shifted path. The result is several glowing lines appearing next to each other, forming the ribbon-like pattern. Ribbon lightning is relatively rare because it requires very specific conditions. There must be strong winds high in the thunderstorm combined with multiple return strokes occurring along the lightning channel. When these conditions align, the lightning flash can create stunning visual patterns in the sky. Photographs of ribbon lightning often show 3 or 4 parallel lightning lines stretching downward from the cloud base. Each line represents a separate return stroke that occurred along a slightly displaced path. This type of lightning provides scientists with valuable insight into wind patterns within thunderstorms. The spacing between the ribbons can even help estimate the speed of winds in the upper parts of the storm. Level 7. Bead lightning. Bead lightning is another unusual lightning phenomenon that appears shortly after a lightning bolt fades. Instead of disappearing instantly, the lightning channel sometimes breaks into a series of glowing segments that resemble beads along a string. These glowing beads form when sections of the lightning channel cool and fade at different rates. As the superheated plasma within the channel begins to lose energy, some areas dim faster than others. The remaining bright segments appear as small glowing spots along the former path of the lightning bolt. This effect usually lasts only a fraction of a second, which makes it difficult to observe without high-speed photography. However, when captured on camera, bead lightning creates a striking visual effect where the lightning channel appears dotted with bright points of light. Scientists believe that irregularities in the plasma channel cause certain sections to remain hotter and more conductive than others. These hot spots continue glowing briefly after the rest of the channel fades, creating the bead-like pattern. Bead lightning often occurs near the end of powerful lightning flashes that contain multiple return strokes. As the electrical current weakens and the channel cools, the glowing plasma breaks apart into these isolated segments. Although bead lightning is not dangerous in itself, it represents another fascinating stage in the life cycle of a lightning discharge. It shows how the intense energy of lightning gradually dissipates after the main flash has passed. Level 8. Staccato lightning. Staccato lightning is a distinctive type of lightning that appears as a single, extremely bright flash that lasts only a brief moment. Unlike many lightning flashes that flicker multiple times, staccato lightning usually consists of just one powerful burst of light. These lightning strikes are often described as having a very sharp and sudden appearance. The bolt may seem thicker and brighter than normal lightning, and is usually followed by an especially loud clap of thunder. Staccato lightning is often associated with positive lightning strikes, which carry larger amounts of electrical energy. Because the strike occurs in a single powerful pulse rather than multiple smaller strokes, the flash appears more intense and abrupt. These lightning bolts are frequently seen during strong thunderstorms with powerful electrical fields. They may strike the ground or travel between clouds, but their defining feature is the sudden and explosive appearance of the flash. Due to their strength, staccato lightning strikes can be particularly dangerous. They often carry high electrical currents and can cause significant damage when they strike the ground. The dramatic brightness and sharp appearance of staccato lightning make it one of the most striking forms of lightning observed during intense storms. Level 9. Ball lightning. Among all reported lightning phenomena, ball lightning is one of the rarest and most mysterious. Instead of appearing as a fast-moving bolt, ball lightning is described as a glowing sphere of light that floats through the air. Witnesses often report seeing bright balls ranging from the size of a golf ball to the size of a basketball. These glowing spheres can appear during or shortly after lightning storms, and sometimes last for several seconds before fading away. Unlike typical lightning flashes that last only a fraction of a second, ball lightning seems to move slowly and calmly through the air. Some reports describe it drifting across fields, hovering near the ground, or even passing through open windows into buildings. In many accounts, the glowing sphere eventually disappears silently, while in others, it ends with a small explosion or sudden flash. Because ball lightning appears so rarely and unpredictably, scientists have struggled to study it directly. Most evidence comes from eyewitness reports and occasional photographs or videos. Despite this, researchers have proposed several theories about how ball lightning might form. One idea suggests that ball lightning may be a pocket of plasma created by a lightning strike that becomes temporarily trapped in a stable structure. Another theory proposes that chemical reactions in the air or in vaporized soil particles could create glowing spheres that float briefly before dissipating. Laboratory experiments have even produced small glowing plasma spheres under controlled conditions, which may help scientists better understand how ball lightning could form in nature. However, there is still no single explanation that fully accounts for all the reported observations. Ball lightning remains one of the most intriguing atmospheric mysteries. Even though it is extremely rare compared to ordinary lightning, its unusual behavior continues to fascinate scientists and storm observers alike. Level 10. Upper atmospheric lightning, sprites, jets, and elves. High above thunderstorms, far above the cloud tops, a completely different category of lightning can occur. These events take place in the upper atmosphere and are known collectively as transient luminous events. Unlike ordinary lightning, which usually occurs within or below storm clouds, these discharges happen at altitudes between roughly 40 and 100 kilometers above the Earth's surface. One of the most well-known types of upper atmospheric lightning is called a sprite. Sprites appear as large red flashes high above thunderstorms and often resemble glowing jellyfish or branching columns of light. They can extend vertically for tens of kilometers and usually last only a few milliseconds. Sprites are triggered by powerful lightning strikes below, particularly strong positive cloud-to-ground lightning. When these strikes release large amounts of electrical energy, they can disturb the electric field in the upper atmosphere and trigger a sprite. Another type of upper atmospheric lightning is the blue jet. Blue jets appear as narrow cones of blue light that shoot upward from the top of thunderclouds toward the stratosphere. Unlike sprites, which appear much higher in the atmosphere, blue jets originate near the cloud tops and travel upward for tens of kilometers. They move incredibly fast and can extend far above the storm before fading. There are also phenomena known as elves, which are extremely brief flashes of light that expand outward in a ring shape above thunderstorms. Elves are caused when powerful lightning strikes produce electromagnetic pulses that interact with the upper atmosphere. These pulses briefly excite molecules high in the atmosphere, creating a rapidly expanding disk of light that lasts only a few thousandths of a second. For many years, these upper atmospheric lightning events were completely unknown because they occur above storm clouds and are difficult to see from the ground. They were only discovered in the late 20th century when scientists began observing thunderstorms with sensitive cameras and instruments. Since then, satellites and high-speed imaging systems have helped researchers learn more about how these unusual electrical events occur. These discoveries revealed that thunderstorms influence not only the lower atmosphere where weather occurs, but also the upper layers of the atmosphere far above the clouds. Conclusion: lightning may appear as a simple flash during a storm, but in reality, it comes in many different forms, from common intra-cloud lightning hidden within storm clouds to powerful cloud-to-ground strikes that reach the Earth's surface. Lightning displays a wide range of behaviors depending on the conditions inside a thunderstorm. Some lightning types, such as forked lightning or ribbon lightning, create dramatic patterns across the sky as electrical channels branch and shift within turbulent storm winds. Others, like sheet lightning, illuminate entire clouds with soft flashes that reveal the hidden electrical activity taking place within the storm. Rarer forms of lightning show just how complex atmospheric electricity can be. Ball lightning continues to puzzle scientists with its mysterious floating spheres of light, while upper atmospheric phenomena such as sprites and blue jets reveal that lightning can extend far above storm clouds into the upper atmosphere. Each lightning flash represents the sudden release of enormous electrical energy that is built up inside a thunderstorm. By studying the different types of lightning, scientists gain insight into the complex electrical systems that power storms and shape Earth's atmosphere. Even after centuries of observation, lightning remains one of nature's most fascinating and powerful displays. Every storm that lights up the sky reminds us that the atmosphere above us is filled with energy, constantly moving and balancing itself in brilliant flashes of light.